Good afternoon. I expect more to attend the lecture in this week too because there may be some problem about webcast. Have you aware of that? Did you able to access the webcast? Yes. After Friday. No. Okay. I please notice that I changed the web page or the course website. Instead of ST2334, now I change to ST2334_1. Why have to make such change? Okay, so the published website for this group is ST2334_1 in IVLE as well as Luminous. Now here's the problem. The webcast is supposed to link to the ST2334, which can be accessed by all the students in ST2334. So I changed it, but somehow it's not under my control. So I asked the CIT try to work on it. So you may not be able to access to the webcast, maybe for a few days until they solve the problem, or help me to redirect or change it to ST2334_1. So tolerate for not able to access to webcast. I don't know whether you watch the webcast immediately after the lecture. So wait for a few days. All right. Second thing about the midterm test. I told you that it is in week 7, but let me be more specific. Tentatively, it will be held on standard date of week 7. I think, if I'm not wrong, it is 9th of March. All right, it's tentative. It depends on whether we can get the venue. So the midterm test, check whether this is correct. It's a Saturday morning till noon. Okay, we try to arrange for the time, get the venue. So it's Saturday. Is it 9th of March? Correct, right? So just let you know. So it's week 7, Saturday. You may have a few tests on that day, I don't know. But because we have 3 groups here, so we have to choose a date that is likely to be accommodate for most of you. So tentatively, it's still tentative, it's March, 9th of March. It's either 10:30 or 11:30. It's a 1-hour test. All right. What are the topics or what are the scopes for the midterm test? It's too early to tell you. All right. But chapter 1 must be there. Chapter 2 most likely be there. Chapter 3 depends. All right. Okay. Any other questions? If no, then we start our lecture. So last week, in the last lecture, we talked about combination permutation. So it's important that you have to make use of the permutation and combinations. And we finished with a high note or very difficult note. We talked about binomial coefficients. All right. Basically, you don't care about the name, but what we mean is that, okay, if you want to choose R objects from N objects, the number of ways that you can choose is the same as you choose M minus R objects from M objects. So it's the same. Oh, thank you. Okay, so Okay. So the web course website ST2334_1 and the midterm test 9th of March. Tentative. I better write it down. Tentative. All right. It's Saturday morning till noon. All right. 9th of March, week 7. So, so the number of ways to choose R out of n objects is the same as to choose n minus R objects out of n objects. So these two are equal. All right? And another thing is to choose n. Wow. So the right-hand side seems very complicated. But in fact, okay, there are at least two ways to look at these formulas. One is from the mathematical formula. You can prove algebraically the left-hand side equal to the right-hand side. All right? Alternatively, you can look at it from the combinatorics, how to choose the things. Now, the left-hand side, I'll choose R out of n. So we have n objects, all right? N objects, then we choose R of them, choose R out of these n objects. So the symbol R choose from n objects is represented by that notation. Now it's the same as, I look at n minus 1 objects and count how many ways that I can choose the R objects. All right? So in other words, I divide this into two parts. One is n minus 1, the other is 1. So if I divide it like that, the one here is the one that I don't want it. So that's why I have to choose, like a simple example is, okay, I have this n objects. All right? So I choose R from this n minus 1 objects, and this one I have to choose it included in my sample, but this is not what I want. So it's the same as you choose n minus 1 objects, choose R objects out of n minus 1 times 1 choose 1. 1 choose 0, sorry. You don't choose anything. All right? So this remaining one, I won't include it in my sample or in my way. So altogether, it is n minus 1, I choose R, and then the other one I'm not choosing. But then you may ask, so how about if I divide it into n minus 1? This is the one that I want. All right? So in that case, then I have choose R minus 1, and the one that I left behind, I have to include it in the sample. All right? So this is how you interpret it. You choose R out of n. I can do it in the following way. I divide it into n minus 1 and 1. So the one can be the item I want, or the item that I don't want. So if it's the item I don't want, then the n minus 1, I have to choose all the R that I want. So it's n minus 1, I choose R, times the remaining one, I don't want it. So choose 0 from the remaining one. Alternatively, I can divide it into n minus 1 and 1. The 1 is the one that I want. That one must be included. So in other words, the n minus 1, I have to choose R minus 1. The two are mutually exclusive. All right? So I have to add them. This is how I get R objects out of n objects. All right? So that is from the probability or from the combinatorial point of view to show that. So you have to understand. If you appreciate it, it will help you to do a lot of the problems. Or you blindly just apply, maybe start from here. You choose n minus 1 factorial over R factorial, n minus 1 minus L factorial, plus n minus 1 factorial, R minus 1 factorial, n minus 1 minus R minus 1 factorial. All right, so this is, you try to simplify it. This is from algebraic point of view. Okay, So these are just some of the identity. The third identity is saying that this one, the R cannot be negative, cannot be bigger than n. It does not make sense. All right? So there's no way that you can choose R from n if R is negative or R is bigger than n. So that's where we stopped last time. All right? Okay, so today we continue. Okay, so let's look at examples. Example 1. Okay, now we have altogether 30 items and divide into two groups, 25 good and 5 bad apples. All right? These are very simple examples, maybe it's so simplistic, but it's very useful. All right, so we have altogether 30 items. And we are going to select 5 out of these 30 items. So the first question to answer is, how many ways I can choose 5 out of 30? In this case, I don't care whether it's good or bad apples. So how many samples can be selected? So this one, I have to choose 5 apples out of 30 apples. And I do not care whether it's good or bad. So that's the first question, or the answer to the first questions. Then the second part is, how many of these samples involve exactly 1 bad apples? Exactly 1 bad apples. Now, so in other words, now instead of looking at 30 apples, now I look at 2 groups. One is 25 good apples and then 5 bad apples. In order to satisfy the condition, what's the condition here? The condition is saying that you have to select exactly 1 bad apple. How many ways that you can select it? So in other words, it cannot be 0 bad apples, cannot be more than 1 bad apples. As with exactly 1. So I have, first of all, among all the 5 bad apples, I have to get 1. How many ways that I can select? So in this case, we are thinking of, you label all these 30 apples with numbers. So out of these 5 bad apples, you select 1. All right? So there are 5 ways to do it. For each of these bad apples being selected, you count how many ways that you can select the good apples. So now you have 25, and you're supposed to get the rest of the samples, which is 4. So that is how many ways that you can select. Now in this case, there are 2 principles that we applied. First of all, the multiplication principle. For each way that you select a bad apples or satisfy the condition about bad apples, then how many ways that you can select the good apples? So that's why you have to multiply them. All right. The second is that, okay, basically I divide the 30 items or 30 apples into 2 groups, good and bad. So the conditions say that 1 bad apples. So I have to apply this condition. But it's understood that the good apples, how many good apples should I choose? 4 out of 25. So that's the second answer. And the third one, at least 2 bad apples. At least. So that means I want to know how many ways I can get 2 bad apples in the sample, or 3 bad apples, 4 and 5 and so. All right? So in other words, I have to know how many ways to get 2 bad, 3 bad, 4 bad, and 5 bad apples. It's a lot of work. But on the other hand, if we work out how many bad apples in the samples, 0 bad apples in the sample and 1 bad apples. This is the complement. All right? So we figure out how many ways that we can got 0 bad apples in the sample, 1 bad apples in the sample. Then subtract this number of ways from the total number of possible ways to select the 5 samples of 5 apples. So this is how we do it. All right. So we choose 1 out of 5, and then the rest. Oh, sorry. This is still the okay. So this is the way. Choose 2 choose 2 out of the 5 bad apples, choose the remaining 3 from the 25 good apples. So this one also. So then we add all this together. So we have to do this 4 times for 4 scenarios. And each one, all right, is to answer the questions at least 2 bad apples. So we have to add them together because all this leads to the answer at least 2 bad apples. So we have to add them together. So the answer is 26126. All right. Alternatively, of course, as I suggest, you can work out the total number of ways. That means I choose, okay, I'm sorry, here I write C. So to make it, so it's 30, we choose 5. This is the number of ways to choose the samples. Minus, all right, 25, I choose 5. 5 bad apples, I choose none. Then minus 25, I choose 4. And then 5, I choose 1. In fact, I've already worked out this one. So it's easy. I just to work. In fact, I worked out this 2. So I just add this, the second term, and then I can find out the answer. All right. So total number of possible ways minus 0 bad apples minus 1 bad apples. Then will be at least 2 bad apples. So the answer should be the same. By the way, maybe you also get the habit to figure out more than 1 ways to get the answer. It helps you to understand. All right. Sometimes it's not just easier to work using 1 way, but they may be the only way to work out. All right. So you try to get 2 or more than 1 way to get the answer. So in this case, what I showed you is 1 way. Add the 2, 3, 4, 5 bad apples ways. Just now I showed you is to get the alternative way, get the 0, get the 1 bad apples in the samples, and then subtract from the overall. Okay. So, so this one, simple example, so I leave it to you to read. Okay, example 3. So we have 9 persons altogether, 4 men and 5 women. We want to form a committee of 3. So remember, we have 4 plus 5, we have 9 persons, and we try to form a committee with 3. So that means we select 3 out of these 9 persons. So with no restrictions, means that I choose 3 out of 9. The 9 is 4 men plus 5 women. All right? Then the second part, with 2 men and 1 woman, if a certain man must be on the committee. So which means that you have to, so this, the 5 women, 3 men, you have to divide into 1 man and 2 men. This 1 man is the certain man. So you have to choose this man. Okay? And then the remaining 2 men, you have to choose 1. Why? Because in my committee, I know only 2 men. So the 1 must be there. Then the other one, I have to choose the remaining quota, 1 man, from the remaining 2 men. All right? So this is the number of ways that you can choose the man, such that a particular man must be in the committee. And then finally, I choose 1 woman out of 5 women. So this is the number of ways to form a committee with certain men to be there. So in other words, I have divided into 3 groups instead of 2 groups. First group, that particular man. Second group, the remaining men. The third group are the women. So 5 women, I choose 1. Okay, just remember what are the conditions. These are the conditions. You have to need 2 men and 1 woman. On top, you also need a certain man. So which is more prominent, more put a more preference. It's that particular man you must be included in the committee. So I have to choose this man in the committee. So 1 choose 1. All right. Then the remaining 2 I choose 1. After that I choose 1 from the 5 women. Okay. The third one, these 2 men they are not They are not talking to each other, so I cannot put them in the same committee. Okay, so, by the way, refuse to serve on the committee together. It does not mean that both of them are out of the committee. No, it simply means that they cannot serve the committee together. So it can be one of them in the committee or none of them in the committee. All right? So this one is harder. So how to divide it? So before we do anything, let's look at how many ways that we can have the committee formed with these two men there. All right? So now I divide it into 2 men and 1 man and then 5 women. So this one, all right, they must be in the committee. And I'm not working on this one. I'm working on they are putting together, not refuse to serve together. I suppose that they have to be together. So I have to choose 2 out of 2. These 2 men must be in the committee. And how about the remaining men? Sorry, cannot be in the committee. Right? And finally, choose 1 woman. How many ways that we can choose 2 men out of 2 men? 1 way. How many ways that we can choose none from the 1 man? Also 1 way. All right? Then, this is. Oh, I'm sorry. Thank you. So, sorry, my mistake. Thank you. So it's 3 men. So this one 2. All right? So, the same applies, except I make a mistake here. So it's to be the remaining 2 men. I choose none of them. All right? So, how many ways can we choose none of them, none of the 2 men? Only 1 way. All right? So, this will be the number of ways that we can choose these 2 men on the committee. So what we want is they're not in the committee, so we just subtract from these possible ways. So that's the answer. Okay, my point is that you have to understand the question. You have hard work if you try to get how many committees formed with A there, how many committees with B there, and then how many with A and B without A and B. So that's a little bit hard. But on the other hand, if you work on 2 men together and then try to subtract from the total number of ways. Yeah. Exactly what? All right. Okay. You are right. You see? Thank you. So I forgot there's still restrictions. You have to have 2 men and 1 woman. That's what we want. All right? Not without restrictions. So choose 3 out of 9 is wrong. So the total number of ways is to choose 2 men from the 4 men and choose 1 woman from the 5 women. Thank you. All right. You see? So the lesson is remember the conditions, remember the constraint. If you ignore it, you make a mistake. All right? It's really a mistake, not 10. Okay. Next one. So we have altogether 20 items, and 8 items have certain properties, and the remaining do not have this property. What is this property? Have cracks, have some problems. All right? So 8 sort of spoil, while the remaining are supposed to be normal. So we select 5 buses out of 20. All right? This one I'm going for send for inspection. What is the conditions on this? The way that we choose? Nothing except that we choose 5. Sorry, we choose 8. 8 out of 20. 8 out of 20. All right? So choose 5. Choose 5 out of 20. 8 is the number that has problem. So we choose 5 out of 20. No conditions, just randomly select 5 out of these 20. And these 5 buses will send for inspection. So that's the number of ways. Then, now we want to know how many samples, how many ways that we can have a sample with 4 buses with cracks. So it's simple. You have divide your 20 buses into 2 groups, one with cracks, one without cracks. So for those have cracks, 8 of them, you choose 4. And then for remaining one, you choose how many? 1. So that these 2 numbers add together is the number of items that you have. Altogether 20 buses. And the second number, 4 and 1, add together is the sample, the size of your sample. How many you want. That is the R. So in other words, you can think of it, 8 plus 12 is your N, while 4 plus 1 is R. Your number of items that you want to select from N. Why multiply? Why we multiply them? Because the number of ways that you choose the 4 cracked buses, there are so many other ways that you can select the non-cracked buses. So choose 1 out of the 12. All right? So this one, where I stand up, the objective here is that, okay, to illustrate, I have a deck of cards, altogether 52 cards. And I divide these 52 cards into 4 groups. And what are these 4 groups? Basically, these are the 4 suits. You see, the number of ways that you divide your cards depends on the question. Now the question, I want to choose the hands. The way that I define it is how many hearts, how many clubs, how many spades that I want. So I divide this deck of cards, 52. 52, ignore those jokers and other things. So that's 52 cards, all right, into 4 groups. So I choose 4 spades from 13 spades and choose 13. So this 13 referring to 13 spades, 13 hearts, 13 diamonds, and 13 cups. Oh, sorry. Okay, this is 13 spades. This one referring to the 13 diamonds, 13 clubs, and 13 hearts. All right. So each one I choose according to the number specified here, and then multiply them. Okay. So we talk about this, how to count. Okay. Now we move on to talk about probabilities. So what is probability? One way is through the experience, through the experiment. So we use this relative frequency. All right. So basically, a probability basically is a number associated with this event. How much we measure how certain, all right, or the degree of certainty that we believe, all right, how it occurs. So measure how likely the event A occurs. That is called probability. All right. There are many ways to define this probability of a given event. The most commonly used is the one that we'll discuss later. But this one, we start with something that is more practical through experiments. So use the relative frequency. So example is like this: toss a die. What's the chance getting a 1 out of 6? So it's 1 over 6. So that one we base on certain assumption and probability arguments. Here, what we can do is I toss the die 1 million times and then see how many times I got 1. So that is the frequency over the number of experiments, number of times of the experiments that we do. That is called relative frequency. So NA over N. So that's how we define it. All right. The event or the probability of event A is the number of times that I got event A out of n times of the experiment that we do. So this is how we define our relative frequency, define the probability. So the relative frequency satisfies these assumptions. So because it's relative, so it has to be between 0 and 1. It cannot be bigger than 1. You cannot have number of times that you got A. It's more than the number of times that you have the experiments. And it cannot be negative. At most, at least it is 0. So it's between 0 and 1. And if A occurs every time, then f of A equal 1. So which means that basically the event A is you cover all the possible outcomes. All right. So if occurs none, all right, never occurs, then f of A equals 0. All right. So I just don't write as probability of A. I just write it as the relative frequency. But basically it means the probability of A. But we define or we use the relative frequency as the probability of A. All right, so if we have two mutually exclusive events, then the relative frequency of A union B is equal to the number of A, or relative frequency of A plus relative frequency of B. Just like I want to have, what's the probability of getting 1 and 2? Or 1 or 2, sorry, 1 or 2. So basically I just count how many times I got a 1 and how many times I got a 2, add them together, and then divide by the number of ways that we do the experiment. A number of times that we do the experiment. So this FA is supposed to be stabilized. What it means is that if you just toss the die 10 times, the number of A's will be can be 0, 1, 2, 3, up to 10. All right? It should be about 1.6 times. But you won't see. You see maybe 0 times out of 10 times you got a 1, or 1 times you got a 1, or 3 times out of 10 times you got a 1. All right? So it's a number. But this number, all right, will change. All right? You can type another 10 times, toss another 10 times, may have a different answer. So in order to make it more or less the same, what we have to do, you have to, okay, repeat many, many times. That means your n should be big, so that the n A over n will be more or less the same. So if you toss the die 1 million times, then it should be about 166,666, around that number of times that you will get a 1. All right? So that's what I mean by stabilized. Okay, so that is the relative frequency approach. So now we move on to talk about the definition of probability using the sample space and the sample points. All right, so the sample space, S, all right, and A is a subset of it. So the probability of A, represented by this notation, I use probability of A. All right, and then the collection of all events is by this P. So basically, it just a set collect all the possible events. Then this probability of an event A has satisfied these 3 axioms. This is important in the sense that this is the foundation for us to derive all other probabilities properties, which may be more useful to you. All right, so the first one simply saying very simple thing. It's just saying that your probability of an event is between 0 and 1. It lies between 0 and 1, inclusive. So the lesson is that if you compute the probability of an event and turn out to be negative, must be wrong. Bigger than 1 must be wrong, no exception. All right, so remember that is the basic properties. Okay, the second axiom is that the probability of S has to be 1. That means for the sample space, remember what is the sample space? Sample space is the set of all possible sample points. So the probability of S means that some of this sample point must occur. So probability of S equal to 1. Axiom 3 is more complicated. First of all, infinity. When you see infinity, it's headache. But think of it, It's basically saying that, okay, I have A1, A2, A3, all these events until many of them. So that's why I have A infinity. Okay, we don't have A infinity, but this set goes on and on. On top, these events are mutually exclusive. That means they're disjoint. So any two of them, they have no common sample point. Common sample point. All right? So this is what it means. Any I and j such that AI and AJ have no intersection. Then, here's the results. The probability of the union of all these events is equal to the sum of the probabilities of individual events. All right? Yeah. Why bother? On the right-hand side is a probability of one event. And what is this event? This event is the union of all these A1 up to many events. But there are some conditions on this one. All these AIs are mutually exclusive. They cannot have overlapping. Then, to translate it, it's the same as the sum of the probabilities. The right-hand side is the sum of the probabilities of what? Of each individual event. Each individual event. So in particular, for two mutually exclusive events, you will have these properties. So this is very important. This is not true in general. The statement, the last line, the last statement, is not true in general. Only when the conditions A and B are mutually exclusive, then this is true. Then this is true. I don't know whether you remember or you come across this one. You familiar with this one? Right? This one is not part of the axioms. This is one of the properties about probability, and it can be derived from these axioms. All right? So the axioms only apply to mutually exclusive events, infinite number of them, union them, and find the probability is the same as the sum of the probability of each individual event. Okay, so now we try to make use of those axioms to solve some problems. So we know that toss a coin, head or tail, what is the chance getting a head if the coin is fair? You know it's half. But my question is, how do we get half? Why have to answer such questions? Because that will help you to understand better about the axioms, how it can be done. So basically, you have these two events, which is a sample space. When you toss the coin, there are only two possible outcomes, head and tails. So that consists of the sample space. Not only that, H and T, the intersection, if you have a head, you cannot have a tail. So it's an empty set. All right? Now, then, axiom 2, saying that probability of H equal to S equal to 1. So the union of these two probabilities, these two events, the probability is equal to 1. At the same time, apply axiom 3. How to use axiom 3? Axiom 3 have A1, A2 up to A infinity. How to do it? So I put A1 equal A, A2 equal B. How about A3? Empty set. The rest, I put empty set. So when the union all the rest, you can ignore the rest. The rest is nothing. So I apply axiom 3 by making use of A1 equal to A, A2 equal to B, A3, and so on. All this will be in empty set. So the union of all this basically is A union B. All right? In fact, I also, okay, let's trust me, probability of empty set equal to 0. So we'll prove that later. But probability of empty set equals 0. So probability A union B, because A union B or head and tail, I should put this as head, this as tail. All right, then it's clear that they are mutually exclusive, so it's equal to the two together. So this also implies that probability of H plus probability of T equal to 1 because of the axiom 3. All right, so finally, because they're fair, so that means these two probabilities has to be equal. So two numbers have to be the same and add up equal to 1. It must be half. So the probability of getting a head is half. These are all derived from the axioms. So similarly, if you want to have the condition twice likely to get a head, then that means instead of probability of H equal probability of T, fair, now this one implies probability of head equal to twice of probability of having a tails. So substitute this in, you will get the answer 2/3 for head and 1/3 for the tails. Okay, I skip this one. Out. Okay. So I still need this one, A and C. So what is A? A is 2, 4, 6. Okay, let me write it down. A is 2, 4, and 6, while C is divisible by 3. Divisible by 3. Divisible by 3. So that means 3, 3, and 6. All right? Now find the probability of C. So, so this one, all right, probability of C. So it's equal to 2 over 6. So number of ways favor is 2, and number of ways is, possible ways is 6, so 2 over 6. Now, my point here is that A union C does not equal to probability of A plus probability of C. Why? Because probability of A intersect C is not empty set. All right? So just remember, A union C, because A and C are not mutually exclusive, then you cannot just add two probability. You get too much. You have to do something. But my point is that you don't need to, okay, what we do is to consider A union C. All right? So which is a set with 2, 3, 4, 5, 6. This is C. All right? And this 2, 4, 6 is A. So union of them is 2, 3, 4, 6. So it's 2/3. The probability is 2/3. Which is not the same as probability A plus probability of C. Okay? This is one way to get the probability of A union C. We will see. All right? This can also be computed as probability of A plus probability of C minus probability of A intersect C. So that is another way to get the answer. What's the difference between these two? This one, I work out the event. What are the sample points in the event? This one, I don't work out the sample points in this event. I work out the probability of A, probability of C, and the probability of A intersect C. So that's an alternate way to get the answer. Which one to use? Depends on what you have. All right? So you can use either way in this example, but you may have to work hard on what is probability of A, what is probability of C, and what is probability of A intersect C. Okay, now these properties are useful. All right, you better get used to or remember or try to make use of these properties. So the first one is probability of empty set equal to 0. Yeah, I think it's very confusing. What is properties? What is the axioms? So basically, axiom is the basic properties that you don't challenge. You just accept it. Well, the properties here, from this one onward, 1, 2, I think I have 6 properties, basic properties. All this can be proved from whatever we have for the axioms. All right? So Probability of empty set equal to 0. So what we do is just make A1 empty set, A2 empty set, and so on. So the left-hand side, the union of all the empty set is just empty set. All right? So apply axiom 3. So it's equal to the sum of the probability of AI. So it's sum of the probability of empty set. Now, many of you are taking it for granted. If I have a number, okay, A equal to A plus A plus A, infinite number of them. So what is A? Zero. A has to be 0. All right? For those who have some idea about this group theory, so 0 and 1 are two very beautiful numbers. 0 is the additive identity. That means whatever number add to it is the same as that number. 1 is the multiplicative identity. Whatever number multiplied to 1 will get back itself. All right? So now I have 0 plus, I have probability of empty set plus probability of empty set. So you can think of it, when you add it to itself, it's equal to itself. So this number has to be the additive identity, which is 0. So that's why it leads to 0. All right? This is the only number, because it's additive identity, that will give you the left-hand side equal to the right-hand side. The left-hand side equal to the right-hand side. This one, add many, many times, is still equal to itself. So that's the only number, 0. All right? So we proved the first identity. Probability empty set equal to 0. Second one, mutually exclusive. Yeah, it looks like the axiom 3. What's the difference between this and the axiom 3? We only have finite of it. So you see, axiom 3 is so powerful. It covers every AI, so long as they're mutually exclusive. So I make use of the axiom 3, make it a special case. How special it is. I consider AN plus 1 equal to empty set. So AN plus 1 is not any set but empty set. AN plus 2 empty set. The rest are empty set. So then I can apply the results of the property 1 as well as the axiom 3. So I get the answer. All right? So, you see? This one equal because I treat AN plus 1, AN plus 2, all this empty set. All right. The third property is probability of A complement equal to 1 minus probability of A. So this one make use of the properties of events. S is equal to A union A complement, and A intersect A complement is empty set. So basically, this is my S, this is my A, and this is my A complement. Or if you don't like it, A, and the outside one is A complement. No intersection, and the union is equal to the sample space. So, probability S equal to this one, and because these two are mutually exclusive, so it's equal to probability A plus probability A complement. This one, we make use of the property that we just shown, the property 2, all right? And this is equal to 1. Therefore, probability A equal to 1 minus this probability. So a lot of things you take it for granted, but in fact it can be proved through the axioms. And in fact, yeah. So this is another very useful property. Probability of event is equal to probability of A intercept B and probability of A intercept B complement. What I want you to know or aware of, all right? If I draw the Venn diagram, it's very straightforward. But what I want you to know is that, okay, A, in fact, okay, the picture is like this. This is S, this is A, and this is B. So basically, I divide A into two parts, two mutually exclusive parts. That means there's no overlap. So first part is this part. What is this part? This part is common to, is in A, but not in B. So this part is A common with B, A intercept B complement. All right? In A, but not in B. So that is the part. While the other part of A is common to B. And these two are mutually exclusive. So that's why probability of A equal to probability A intercept B plus probability A intercept B complement. Right? I break down this A into two parts, A common to B and A common to B complement. So this is how we got the properties. Then come this famous identity. Probability A union B equal to probability A plus probability B minus probability A intercept B. All right? How to do it? So, it's another trick. A union B. So, what it means is that, okay, we look at those A union B, right? So, it's the B part plus something, which is this part. This part is not A, but A intercept B complement. All right? So, it's equal to this. But this B intercept A intercept B complement is empty set. Maybe by looking at the Venn diagram, you know that this is true. But what I want you to also aware is that, look at it. B, this means that you try to find something common to B and common to A and common to B complement, which does not exist. You cannot find something in B as well as in B complement. So this must be an empty set. This is an empty set. All right. So probability A union B is probability B plus probability A intercept B complement. But what is probability A intercept B complement? It's equal to probability A minus probability A intercept B. So that's how we arrive. So this part is break down into these two. So that's how we get the property. Okay, although you will not be asked, I believe that, you will not be asked to prove this, all right? But it just asks you to apply it. So you have to know when to apply it, how to apply it, all right? So, so basically, you make use of A union B is break down into two mutually exclusive parts. One is B, while the other is A intercept B complement. You can try to show it yourself by consider A union B intercept A complement. This is also equal to A union B, and then see whether you will arrive at the same answer. Okay. So we extend this to three, union of three events. So it's like this. Add up all the probabilities minus all the possible intersection of two events, and then add back the intersection, probability of intersection of the three events. So it's basically saying that, okay, A, B, C, right? A, B, C. When you add A and B together, you double count this part, which is common to A and B. That's why you have to subtract A and B probability. When you find A and C, so you double count the A and C together. The intersection, you double count it. So you have to subtract it and also subtract the B intersect C. But the problem is that you subtract too much. What happens to this? Common to A, B, and C, you subtract 3 times. Well, you shouldn't. So that's why we add back 1 time. All right? So this is how we interpret that. But basically, you can prove it very simple. You must need some tedious work. I just work on the 2 events. A union, another event is B union C. B union C. So applying the result, so it will be like this. Probability A plus probability B union C, then minus probability A intercept B union C. All right? Then this part, I can write it as this one, applying the two events case. So the only thing that left behind now is to work out this part. What is the probability A, intersection of two events, A and union of B and C. So this one simply saying that it is A intercept B and A intercept C. Those common to A and common to B, and those common to A and common to C. Find the union of them. So immediately, it's just the probability of the union of two events. So you just work on these two. All right, so that's what. So probability of A intercept B union A intercept C. So it's A intercept B plus A intercept C, and then minus the union of this. Common to A intercept B, common to A intercept C. Basically, it's common to A, B, and C. So it is A, B, and C. A intercept B intercept C. All right? Oh. This is called inclusion-exclusion principle, just an extension to what we just discussed. We discussed the union of two events. We discussed union of three events. So you can ask, what's the union of four events, 5 events, and so on? So this principle basically applies to n events. So the idea is that, okay, if I want to find the probability of union of n events, now I did not say that they are mutually exclusive, so they may have they have intersections. So it's equal to the sum of individual probabilities, but we count too much. So I have to subtract the probability of the intersection of any two. All right? Yeah. Wow, what is this? This basically saying that I count all possible ways to present AI intersect AJ. How many of them? So my way to do it is that, okay, I start with I equal to 1. So I consider A1 intersect. The next one is J, I and J. J is from I plus 1. So A1 intersect A2, and then A1 intersect A3, A1 intersect A4, up to A1 intersect AN. This is what it means. J from I plus 1. So that's the beginning of the subscript until the J equal to N. So it's from J equal to I plus 1, J equal to I plus 2, J equal to I plus 3, and so on up to J equal to N. So that's what it means. Only when I equal to 1. Then after that, you change I from 1 to 2. So it's A2 intersect A. This one is not 1, not 2, but has to be 2 plus 1. So A3. Then A4 and so on. A2 intersect AN. It's only if I equal to 2. Then you have A equal to 3. Start with A4 and so on. So that's why you want to write it down. I don't want. So we use this, what we call double submission sign. So it reads like this. You fixed I, and I range from 1 to n minus 1. Why to n minus 1? Why not to n? Because if I equal to n, then j cannot be any numbers, because it has to be different. So if I equal to n, j cannot be any number. All right, so we have to reduce it to n minus 1. So similarly, this is to minus then subtract the probability of AI intersect AJ intersect AK, and these are the way that we count IJK. The last one, N. Oh, I don't know whether it's plus or minus. Then I see the pattern. When there are 2, it is minus. When there are 3, it's plus. So when there are N, it should be N plus 1. Let me repeat it. When there are 2 events, this notation is minus. So it's 2 plus 1. All right? So minus 1, 2 plus 1. This one, 3. So if I change this to 3 plus 1, so it's a positive. So the last one is the intersection of n events. So whether this sign is positive or negative, I cannot tell. But I know that it should be equal to -1 to power n plus 1. N plus 1. Can I use n minus 1? Yes. -1 to power n plus 1 is the same as -1 to n power n minus 1. Am I right? -1 to power 7, negative. -1 to power 9, negative. Right? This is n equal to 8 minus 1 and 8 plus 1. So they are the same. All right, so this is called inclusion-exclusion principle. So basically, it is just how to get the union of n events, probability. Last properties that we mentioned here. If A is a subset of B, then probability A is less or equal to probability of B. Seems very natural to any one of us. But we can prove that based on the axioms and the properties that we have discussed. So what it means is that I use B, break this B into B union B intersect A. This is one event. Union B intersect A complement. Remember, B has two parts. This is B common to A, B intersect A complement. This part is B common to A, or A intercept B. And they are mutually exclusive. Okay. So this one is no common point. But on the other hand, A is a subset of B. So B intersect A must equal to A. All right. We are saying that A is included in B. So A intercept B is basically A. All right. So this reduced to A union B intersect A complement. And all right, we are looking at the union of these two and the intersection of the same two. The intersection is empty set. Why empty set? Because A and A complement are empty set. So then probability of B, because they are mutually exclusive, therefore the probability of B equal to probability of probability A plus probability B intersect A complement. And this has to be bigger or equal to probability A. Why? Why is because this one, remember probability of any event has to be greater or equal to 0. So probability of A plus something which is bigger or equal to 0. This means that it has to be bigger or equal to probability of A. This one is bigger or equal to 0. You are adding something which is bigger or equal to 0. So therefore, this must be bigger or equal to this number. So my point is, it seems very straightforward, very pretty simple identity. If A is a subset of B, then probability of A is less or equal to probability of B. But we can use the properties of probability to prove that. Okay, so this example 1 straightforward. Example 2. Okay, example 2. So we have this professor, statisticians. So the work that they do, all right, there are 3 categories, A, B, and C. Doing research, doing professional consultation, or data collection and analysis. All right. So this add up 140%. So how come it's 140%? Okay, so when you look at it, you may think that, okay, each statistician can only do one job. But no, they can do 2 or more. That means some statisticians, some of this mentioned here, statisticians, they may do more than one of these categories job. All right, so that's why it does not add up to 100%. Because there's some common. So this 64 may double count, all right? Or 40. Okay, so here it tells us that, okay, 10% involve all 3 activities, 15% A and C, 70% A and B. What I did not mention is what happened to B and C. This is what we are asked to find. What is the probability that involved in only B and C? All right. Now this is important. Without these assumptions, what does this assumption mean? Probability of A union B union C equal to 1. What is it? That means that any solutions, yes, you're right. Any solutions must at least must work on one of these three categories. No exceptions. Must belong to one of these. Either A, B, or C, or any two or three of them. What does it mean? It means that there are no fourth choices for this group of statisticians. All right? No fourth choices. Only these three choices. This is the assumption that we make. Without these assumptions, we cannot proceed because there may be a D category working on something else. All right? Okay, so there may be a D or maybe doing tuition. All right, D. So we don't know whether there's any fourth categories. So, but with these assumptions, this assumption simply means that any one of these statisticians must work on at least one of these categories. So with this, we can proceed to find the probability. So these are given to us, and also one given to us is this equal to 1. All right? So we can work out all this except probability of B intersect C. So the answer is 18%. So 18% of the statisticians work on both B and C categories. They're doing data analysis as well as doing consultation work. Okay, so my point is don't take it for granted this probability of A union B union C equal to 1. So either it's given in the questions or you're pretty sure there are no other beyond these three categories, no fourth categories of work for this group of statisticians. Okay, so so the event that we are talking about is the number of cars arrive at a petrol station during a 30 minutes interval, a certain 30 minutes interval. 0 car, 1 car, 2 car, 3 cars, 4 cars, and or 5 or more cars. All right? So it covers all the possible number of cars arriving. 0 cars, 1, 2, 3, 4, and suppose 5, 6, 7, you can keep the list going. But we just group all the number 5, 6, 7, and so on into one group called 5 or more. So these are the corresponding probabilities. Now because all these events, they're altogether 6 events here. So all these are covering, okay, all these are mutually exclusive. Not only that, they are also exhaustive. For which I means that any time that the number of cars visiting this gas station will be one of these numbers, one of these possible events, 0, 1, 2, 3, 4, 5 or more. All right? So the corresponding probability, so all this should add up equal to 1. If it's not 1, then something wrong. I want you to see the link. So these are the events, possible events. The number of cars visiting this gas station is either 0, no cars during this period, or 1 car, or 2 cars, and so on. So 5, 6, 7, 8, 9, all this will be grouped into one group called 5 or more. All right? So the probability of 5 or more cars visiting this gas station is 0.17. So all this probability add up to equal to 1. So find the probability of more than 2 cars. So you just add up more than 2 cars, not including 2 cars. So you add 3, 4, and 5 and more. So add all this together. We can add because all these are mutually exclusive events. At most 4 cars, so you also this one should 5, sorry, and most 4 cars. So you just find out the chance of 5 or more cars and then subtract from 1. That's the easier way to get. All right? So you see, this is to add up 0 car, 1 car, 2 cars, 3 cars, 4 cars. They are mutually exclusive, so I add up all the probabilities. Alternatively, I just get 5 or more cars probability and then subtract from 1. So the same answer. Which one is easy? Of course, this is easier. I don't know. Add up 5 numbers. When you press your calculator, you may make mistakes. So you get the wrong answer. All right. So I skip this example. This example basically, someone go for a pageant. Okay, that many titles. All right, Miss. This is a hall pageant, so it's Miss Hall A. There are also Miss Photogenics or Miss Friendship. There are many titles. So basically, it just gives us the probability of an individual Audrey. Okay, what's the chance that she got to the crown, or the chance that he got the photogenic, all right, and the chance that you win both. So with all this, and you work out the answer for these questions. What's the probability at least one of the 2 titles? Oh, one of the 2. That means it can be one, can be this one, or can be both. All right. So it's harder to get these 3 events probability. But instead, maybe easier to work out what's the chance that she could not get any of the 2. I mean, what I mean is that the intercept at least. Okay. So what I mean is that you get A union B minus A only 1. This is only 1. So A union B minus probability A intercept B. So I use this notation. A better way, in fact, is to say that I want A but not B. I want B but not A. All right? So this is get the A, this got the B, and then union of the 2. So this is the more relevant way to write it instead of using this subtraction. And of course, you can show that the probability of this one is the same as this one. Right. But anyway, this may be more appealing to most of you with A and B. So now I want A but not B, so this part. I want B but not A, so this part. So the union of these 2 is only 1. Then only one title. All right? Only 1 title. So it's A union B minus the A intercept B. Oh, birthday problem. This is the next 2 examples, example 5 and example 6, are very interesting problems. Okay, what it says is that, okay, in a room with n people, what is the probability that at least two of them will have the same birthday? All right? So, if you find someone in the room claiming that, quite confident that there are, in fact, in this room, it's very likely, not very, but the chance of having 2 of you have the same birthday is very high. How do we know? I'm not guessing, I can show you. All right? So if there are n people, what's the probability that at least 2 people with the same birthday? So at least 2 people have the same birthday. Very difficult to work on that probability. But the probability of getting no 2 people have the same birthday is much, much easier. Right? So I start with one person, so his birthday can be any one of the 365 days. I will assume no leap years, equally likely, right? So the possible number of birthdays, all right, combination is 365 to power n. So each one can have one of the 365 days. So it's 365 over n, to power n. But now I want to find out how many ways that no two are the same birthday. So, the first guy, 365. Then the next guy, the second one, cannot have the same birthday as his, so 364. Next, 363. Until 365 minus how many? I have n people. So what is this number? First one, 365 minus 0. Second person, 365 minus 1. 365 minus 2. So this one is 365 minus n minus 1. This is the number of ways that we get no two of the people have the same birthday. So the probability will be this one divided by 565 to power n. So this is the probability. Or you can write it like that. That is the probability. All right? So, how does it look like? So we have to substitute some n to get a taste of this formula. So here is the formula. So, the probability of getting more than half of, okay. This is the Qn. Qn is the probability of A complement, the one that we just have. Okay, 1 minus 364 over 365 times 363 over 365 and so on. So that is the number, and this is the probability of getting at least two of the people getting the same birthday. It can be 3, can be 4, but at least 2. So with 23 persons, the chance of getting 2 out of these 23 persons having the same birthday, the probability is more than half. More than half. It's just like toss a coin. It's not that rare, all right? In fact, 50. If I got 50, the chance is 97%. Here I'm more than 50, right? So it's very likely that I will find at least 2 persons that have the same birthday. So it's not that strange. So you check with, if you have 50 friends, you check, it's likely that you will have the same birthdays. Sorry, I made a mistake here. I'm sorry. What's the mistakes? Here is in a room with 50 persons. I did not say they must have the same birthday as mine. Any 2 of them, or more than 2 of them, can have the same birthday. I did not say which day. But when I said, okay, I look at my friend, I have 50 friends, how come I don't have friends with, because I'm talking about my birthday, I specify the date. All right, so that's different. All right, this one referring to a group of people, I find at least 2 have the same birthday. So here is the example 6. We call it inverse probability, birthday probability. Find someone who share the same birthday as you. How many persons we need? All right. So if I want to check among this group whose birthday is the same as mine, the probability may not be that big as compared with the previous one. The previous one is that I look at all of you, I just check whether there are 2 of you or more have the same birthday. All right. It can be any day of the year. But now I'm talking about same birthday as mine. All right, so how to do it? So it's very simple. Again, I try to look for n persons. Ask you whether your birthday is the same as mine. So the chance that you have the same birthday as mine is 1 over 365. So if not, it will be 364 over 365. All right? All right? So then the next guy, I also ask the same question. So the first guy, the probability that he will not have the same birthday as mine is this one. The next guy may be the same birthday as the first guy, but I want to know whether he has the same birthday as mine. So it will be something like this. So I have n guys, so this is the probability. Right? Each one has 364 over 365. Then So this will be the probability that n persons with a birthday different from mine. All right. So same as mine, 1 minus it. I want this to be greater or equal to 0.5. All right. Let me repeat it. I want to work out what's the chance that none of these n persons have the same birthday as mine. So I check the first one. The chance that he does not have the same birthday as mine is 364 over 365. All right. Suppose my birthday is 21st of January. All right. Today. All right. Then check anyone has 21st. So the first one, no, because okay, the chance is 364 over 365. So the next guy also 364 over 365. So I just multiply all this. All right? So that is the chance that have different birthday from mine. So 1 minus it is the chance that it got the probability that it got the same birthday. I want this probability to be greater or equal to 0.5. And how many persons do I need? So this is inequality. Solve for inequality. Very hard. So first of all, we try to simplify it, make n to be one side. So basically it is 0.5 greater or equal to 364 over 365 to power n. Solving inequality just like solving equation. All right, so you have to manipulate. But the problem is that we have the n there, it is in the exponents. How to solve this type of equation or inequalities? You try to push down the n from the exponents. How to do it? Take log. In mathematics or in statistics, when we say take log, it's log base e. So it is n log base e 365 over 364. 364 over 3. And again, this one is log 0.5. Inequality is a little bit more complicated. When you do something, make sure that the inequality direction is still correct. It's not equation. Equation, when you divide both sides by -1, it's still the same equation. But inequality, when you divide by -1, then it will reverse the inequality. When I say 3 is bigger than 2, right? Correct. But if I divide by -1, it becomes -3. This side becomes -2. You cannot have -3 bigger than -2. You have to reverse it, the inequality. Right? So you have to worry about this one. So now I take log, okay. But log 0.5, you are aware that this is a negative number. But anyway, so this one, also a negative number. How do I know it's negative? Because this is less than 1. Log of a number less than 1 will give you negative. All right? So anyway, this is how you get. So n is greater or equal to log 0.5 divided by log 364 over 365. And the answer is 252. What does that mean? It means that I need to have at least 253 persons. In order I can find at least one of them will have a birthday same as mine. And the chance is only slightly bigger than half. If you want to have 95%, how many persons do I need? It's big number. How do I do it? You just change this. If you want 95%, then change this to 0.95. All right? Okay. So example 5 and example 6, the difference is one is just to find the number of persons that they have similar or same birthday. Whilst example 6, I need to find the chance of find someone have the same birthday as mine. All right. So this is what I explained. Okay. Sample space having finite outcomes. This is for us to find the probability. So I start with a more general setting. Later on, we usually assume equal likely setting. So here, we assume the sample space has these outcomes. K of them, finite outcomes. And then each one has a probability pi. So because S equal to each individual AI up to AK, and each of them are these outcomes, so they are mutually exclusive. So the sum of all this probability has to be 1. All right? So an event A, you just look at how many sample points are there and then add up the corresponding probabilities of this sample point. Now, in this case, we don't assume that the outcomes are equally likely. But later on, we'll try to work on equally likely outcomes. So that's why we need some technique to identify equally likely outcomes. A simple example is to toss 2 dice. So if you don't differentiate the die, then the outcome 1, 2 means that one die is 1, the other is 2. But this may mean that the first die is a 1, the second die is a 2, or the first die is a 2, the second die is a 1. So in that case, we have to distinguish them in order to get equally likely. But what we say here is that we don't assume equally likely, but basically just add up. So this is the example. All right? So we look at the sum. So what are the possible outcomes? The possible outcomes are this. They're not equally likely. All right? They're not equally likely. You have to work out each one. What is the probability? In order to do that, basically, you have to add up. Like 4. What are the outcomes corresponding to 4? So 2, 2, 1, 3, and 3, 1. This will give you the sum equal to 4. All right? So in that case, we also assume that each of these are all equally likely, which is a reasonable assumption. So then we get the probability of 4, which is equal to 3 over 36. 3 over 36. All right. So this is how we do it. Okay, so I think example 2 is more or less the same. Just remember, each individual outcome may have an unequal probability. You just have to work out the probability of the sample space. All right. Yeah. So I think I have to stop here. All right. So for the webcast, we try to work it out and hope it works soon. The midterm test tentatively is on the 9th of March, Saturday morning. Tutorial registration for exchange students, please send me an email, indicate your preference. Do you have any problems in registration, tutorial registration? Shouldn't have any problem, right? I will upload the tutorial question soon.